Have you ever glanced down the drain of your kitchen sink? If so, you might have noticed some weird goo in there and probably moved on pretty quickly. But has it ever occurred to you that that goo might be useful? There are microbes, single-celled microscopic organisms in many places. They live with us, within us, on us, and around us, including in that goo in your sink. We can't see them with the naked eye, but they are everywhere. They are busy. As a microbiologist, I have always been interested in what these tiny organisms are doing. Do they live alone? Do they mingle with different types of microbes? Are their communities as dynamic as our cities? Microbes can be pretty particular about where they live, and although new approaches to studying them in the lab are happening all the time, not all microbes thrive in a lab environment. This means that for a long time, what we ended up doing was only studying the microbes that we were able to grow. And we missed a lot of the diversity of microbes that truly exists in the real world. All this changed when new DNA sequencing approaches were developed around the early 2000s. Sequencing DNA involves figuring out the order of the 4 chemical building blocks that make up the DNA molecule. Once we know what order the building blocks are in, we can use this information in a lot of different ways. For my work, the big deal about DNA sequencing is that it allows us to take these microbial communities, sample them directly from their environment, and learn which microbes are probably there based on their unique DNA patterns. This approach, called metagenomics, is based on the comparison of microbial DNA to DNA sequences found in databases, collections of sequences with information about the genes and organisms they come from. Better understanding the genetic sequence of microbes we can't easily grow opens up a lot of possibilities. So what do we do with this? In 2013, I came to NC State and was able to design a new course in which students and I were able to sample an environment and learn about the microbes that lived in that area. We wanted to figure out which microbes are there, about how many of them live in that spot, and what they can do. As I was designing the first run of this course, I had conversations with a colleague of mine, Dr. Rob Dunn, that inspired me to ask a simple question. Which microbes are living in the drain of our kitchen sinks? So that semester, in the fall of 2013, a dozen students and I took cotton swabs and swabbed the drains of kitchen sinks. After extracting the DNA, we found that the cotton swab for one kitchen sink had over 60% of sequences that matched an organism I had never heard about, Delphtiacidovorans. What was this mysterious microbe? Why was it in a sink? With students eagerly watching, I Googled the name and learned something really interesting about Delphtiacidovorans. This little microbe has a superpower. It's able to defend itself against liquid gold, which is normally toxic to microbes, in a unique way. It does this by making a protein that turns tiny amounts of liquid gold into solid gold. We believe it's one of few microbes that is able to do this. Why is this important? Because gold is actually a component of electronic waste, and we have limited supplies of it. Electronic waste contains trace amounts of liquid gold that is too expensive and time-consuming to harvest with traditional methods. But letting this microbe do its work could potentially be an easier, cheaper way to recover important and limited resources from discarded electronic waste, reducing toxins in the environment and increasing our supply of this precious metal. Over the last 7 years, I have worked with inspiring undergraduate students to use metagenomics. Remember, that's comparing DNA sequences in groups of microbes we find to DNA sequences in databases, to study the genomes of microbes from environments to learn more about Delphtiacidovorans and other microbes. We are learning a lot about what these microbes can do, including sticking to metallic surfaces and their origins. I'm working toward figuring out how we can harness the energy from these specific microbes to extract precious metals from discarded electronic waste. If we can move this idea from a possibility to an efficient economical reality, we could be part of a solution to decreasing the negative impact of electronic waste on the health of our planet. As DNA sequencing technology is becoming more powerful and even more portable, we are now able to sample communities of microbes from a variety of different environments, stabilize the sample long enough to bring it to the lab, and isolate DNA from the community to learn which microbes make up this group. The approaches used to obtain DNA from microbial communities and sequence it are constantly evolving. Procedures that were once time-consuming and tricky are now greatly simplified and can be done using automation, lab instruments that reduce manual handling of samples. Automation also allows us to process more and more samples in ways that are consistent and less prone to human error. And as methods improve and we use new technologies, we are now able to catalog microbes from different environments, compare them to databases, sequence their genomes, and learn how to use them to improve our sustainable practices. This is the combination of technology, software, and ever-growing databases that allow us to continuously improve our understanding of the diversity of microbes on our planet, from kitchen sinks to compost. Metagenomics and automation allow us to address global challenges that once seemed almost insurmountable, from determining the microbes that cause disease to identifying sequences that can help us produce medicines. Microbes sometimes get a bad reputation for contributing to disease, but by learning about them and their superpowers, we are finding ways that they can play a role in improving the health of our environment. Does your kitchen sink hold the microbes, genes, and communities that will help us solve future wicked problems?